Around the point where we estimate the density, draw a window whose width is determined by the bandwidth. Count how many observations fall inside that window, then divide by the sample size and the window width. As the window moves, the count changes and traces a density estimate. This resembles a moving histogram, but the window is centered on every evaluation point, rather than tied to a fixed set of bins. Comparing a uniform kernel estimate with a histogram clarifies why the two can look different. A histogram treats every observation within a bin identically and changes abruptly at each bin boundary. The kernel estimate uses a moving neighborhood, so it is not anchored to those boundaries. With a smooth kernel, the resulting curve changes smoothly as well. Neither display is automatically correct. A careful analyst checks whether major features such as asymmetry or tail thickness persist across reasonable bins and bandwidths. Daily equity returns provide a useful application because their distributions are rarely summarized well by a normal curve. A histogram of FTSE 100 returns shows the broad location and spread, while a kernel density estimate gives a smoother view of the center and tails. The purpose is not to decorate the histogram with a line. It is to investigate whether the empirical distribution is sharply peaked, asymmetric, or unusually heavy-tailed, all of which matter for risk measurement and model specification. When reading a financial return density, distinguish visual prominence from probability importance. A tall central peak means many observations are concentrated near typical values, but rare tail events may still dominate loss calculations. A small secondary bump might indicate a genuine mixture of regimes, or it might be sampling noise created by a narrow bandwidth. Kernel estimation is exploratory, not a mechanical proof of multimodality. We should compare bandwidths, inspect the raw observations, and connect apparent features to economic context before drawing conclusions. In IR, a practical workflow begins by cleaning the variable, checking missing and extreme values, and plotting both a histogram and a kernel estimate. The density function can generate evaluation points and estimated heights, while plotting tools can overlay alternative bandwidths. Always record whether returns are expressed as decimals or percentages, because a change of scale changes the numerical bandwidth. Also, avoid letting software defaults become invisible assumptions. A reported curve should be reproducible from an explicit kernel, bandwidth rule, sample period, and transformation. Transformation can help when support or scale is awkward. For a strictly positive variable, smoothing its logarithm may avoid assigning probability to negative values. Returning to the original scale then requires the transformation's Jacobian, so simply relabeling the horizontal axis is incorrect.